Hi guys, welcome to part 3 of functioning ecosystems. Now if you watch part 2, you should have an understanding of food chains, which are the linear representation of energy flow in the different trophic levels. You should know about food webs, which shows a greater amount of connection within or multiple food chains within that ecosystem. And you also looked at biological pyramids, okay? So they can be displayed as numbers, which sometimes are able to be inverted. Also, they show energy, which is never inverted, and biomass, which can have the weird example of being slightly inverted for that phytoplankton and zooplankton, but very rarely otherwise actually are. This lesson we're going to continue looking a bit at energy efficiency sort of in a different way and extend on what you have that previous knowledge. So remember, when calculating energy efficiency or trophic efficiency, you look at the net production of that trophic level divided by the net production of the previous trophic level multiplied by 100. So hopefully you've had a good chance to practice a few of those different calculations. The learning goals for today's lesson. The first one is to construct and analyze simple energy flow diagrams illustrating the movement of energy through ecosystems, including the productivity, gross and net, of the various trophic levels. And then kind of changing gears a little bit, we're going to describe the transfer and transformation of matter as it cycles through ecosystems. So we're going to look at 3 cycles: water, carbon, and nitrogen. Let's get into this. Alright, so energy flow diagrams. What are they? Well, energy flow diagrams are something that maps the path of the sun's energy as it transfers through the trophic levels of an ecosystem. You'll notice here, this is the amount of light energy that you have coming into the system, and these are our different trophic levels. So we have producers, primary consumers, and secondary consumers. I did show you an energy flow diagram in the last lesson. We did one that flowed a different way. They can be shown to flow both ways. Okay, so either your arrow's going this way or your arrow's going across. But they'll be set out in a very similar fashion, where you have the energy coming in, you have your trophic levels, and you'll also have how it's transformed into heat via metabolism, and sometimes they'll contain the amount of energy that's also lost via waste there. So you can see the amount of energy lost via waste from the system, and eventually all this waste energy, well, it will once again still be converted into heat energy here by your detritivores and decomposers as they break down that detritus or that waste material from the different trophic levels. So several key points that I want you to keep in mind when constructing energy flow diagrams, because one of the learning goals is to be able to construct them, and you may be asked to do something like that in an external exam. So the first thing is the arrows show the direction of energy flow and are labeled with the form and quantity of energy they carry. So in that previous one, you notice that the arrows were pointing as you move along the trophic levels, so it is essential in the direction they are pointing. And you'll notice that there was chemical energy, all right, it was labeled, one of them, and we also had some arrows, I'll just draw it up here, that were heat energy as well, okay? So, and there might have been, say, 80,000 for that first one. So when we look at the arrows, they'll tell you the amount. Let's just write 10,000 here, so the quantity and the type of energy, and the arrows will point in the direction that that energy flow goes. So that's an important feature to represent. The boxes used to represent the trophic levels, well, they're in sequence. So here we would have our producers, then our primary consumers, and our secondary consumers. So it is sequenced. Heat energy from metabolic process is lost from each trophic level to the surroundings. So you do have to show that heat energy being lost. You also do have to represent detritivores and decomposers on the sub-trophic level. So that's a level below the other ones, which, as you saw, was down represented as down here, because they are actually very important in the role of energy transformation, because they'll still undergo respiration as they're breaking down that material, and they'll lose some of that energy as heat as well. So it needs to be shown and represented. And the total heat energy lost must equal the amount of chemical energy brought into the system by the producers. So obviously they're going to lose a certain amount of heat energy throughout each different trophic level, and that should equal the amount of energy that was initially brought in by the producers. Sometimes some things can happen which means that's not as efficient, because you're going to get immigration and emigration, stuff like that. But in a closed system, in a perfect ecosystem there, it would actually equal. So when we look at the available energy at each trophic level, it must, as I mentioned, equal the amount of energy entering that trophic level. So let's say here I've got my primary consumers, and we'll just say this is primary consumers. We have 100 joules of energy which they are consuming. So this idea, this is consumption. All right, so they are consuming that amount of energy from the previous trophic level. When we look at what happens here, 65 joules, we'll just say joules, is lost as heat energy via metabolism as a process of respiration. 15 is lost as waste in feces and urine, and then 20 of that is actually assimilated. So that's kind of what they've brought up to be able to use for growth and also reproduction and those type of things. And that's what will be then passed on to the next trophic level. So when we look at the next one, let's say we start off with 20 and we go through this. Well, they might lose 12. Here we'll go 5 there, which means they're going to pass on 3. So that would be something you would show and represent, and you'd have to have your trophic level there. And this is a very simple energy flow diagram which shows where that energy is going. So the arrow is pointing. It's given you what type of energy it is, and it's given you some quantitative values as well. So when you look at this, as I mentioned, the energy available to each trophic level will always equal the amount entering that trophic level minus the total losses to that level. So the losses to energy are metabolic activity, waste, excretion, those type of things there, and they're represented. Going back to an energy flow diagram, and this is the classic example that's used in most textbooks. This is a Silver Springs community trophic efficiency. You can see the units that are used in this one. So you've got kilojoules per meter square per year. And you'll notice, my pen's doing something funny, but other than noticing that, you'll see that here, this is the amount of sunlight, this is the amount of energy that's come into the system. So you can see that the primary, well, I should say the producers, they produce 87,403 joules of energy from that sunlight. You've got the energy that's lost as heat, and you've also got energy lost as waste. You'll notice that the arrow here, which is pointing to the amount that's going to be consumed by that level, and again, it's passed on, and hopefully all of that type of diagram makes sense. This diagram also includes the immigrants, so those who died coming in, and the emigration, so those who actually left that system. So immigrants, those coming in, emigrants, those who are leaving that system there. So we're going to look at a couple of questions. 3, I'm going to go through the answers. You can see if you can do them yourself. Obviously, I'll look at the answers with you and hopefully help you understand and make sense of this energy flow stuff, because it is a bit tricky for some people. So question 1 is going to be calculate the trophic efficiency of the primary consumers. And if you want to go, you can also look at the secondary consumers. Just to test yourself, I will give you the answer for the secondary consumers as well. Determine why immigration and emigration was included at the right of the diagram, and determine if heat losses equal the total energy brought into the system by producers, and comment on your result. So why might it or why might it not equal that total? So going through some answers, so once again, pause if you don't want to see the answers now. Calculate the trophic efficiency of the primary consumers. Remembering the formula for this is the amount or the net production at the primary consumer level divided by, so here I should say, the net production at the that trophic level divided by the net production of the previous trophic level. So looking at our results here, we've got our net production of the primary consumers. So this is 1,609 joules of energy divided by the net production of the previous trophic level, which is this one here. Once you divide those times by 100, you get 11.37. If we're looking at our trophic efficiency of the secondary consumers, so secondary consumer trophic efficiency, it's going to be this one. So that's their net production, 88, divided by the net production of the previous trophic level, which is 1,609. Now remember the difference between net and gross. Gross is the total sort of that's coming in for this one, and net is actually what they are able to pass on once you take on or take out the energy that's lost there. So 88 divided by 1,609. If we go to one decimal place, it's going to be about 5.5%. So looking at question 2. So determine why immigration and emigration was included at the right of the diagram. Now, these are individuals that were not previously in here, for example, with emigration. So they're ones that have actually come into the environment and left the environment, and immigrants are ones who have come into that environment there. So they're included to the right simply because organisms that enter or leave the community, they're going to bring or take resources, i.e. biomass, that total amount of living organic matter with them. And that must actually be accounted for, because otherwise at the end, when I'm doing my mass, I'm going, well, it doesn't all add up. So I do need to take into consideration the energy that's brought into the system, and I do need to consider the energy that was actually lost from that system as well. And last one, determine if heat loss is equal or total energy brought into the system by producers. So as I mentioned previously, the amount of energy brought in by producers, which is here, should equal all of this heat lost when you total it all up. So if we go through this, heat losses, we've got our 50,303 plus 7,938 plus 1,328 plus 55 plus 1,932. So that's the decomposers which are losing that amount of energy from respiring. So when we add them up together, we get 78,834. And this does not equal our total, which was 87,403. So the difference of 8,569, so that's found by taking this one minus that one. So the amount we should have had minus the amount of heat we do have may actually be attributed mostly to emigration. So that and minus the immigrants who died without respiring. Because once we actually total that in, you do get a value very close to this here, okay? And obviously, this is not therefore completely energy efficient because, doesn't have complete energy conservation because we are getting some energy coming in and we are getting some energy loss. It's not a closed system. And as a result of that, the amount of energy brought in by the producers does not actually equal the amount that heat loss that it would in a completely closed system. So kind of changing up a bit. We've looked at trophic efficiency, which compares how efficient going from this trophic level, say primary consumers, to this trophic level, say secondary consumers is. Now what I want to just teach you quickly is production efficiency, which is a different idea. So the amount of chemical energy in consumers' food that is converted into their own new biomass during a given time period is called the secondary production. Alright, so this is the secondary production, and this is the amount of chemical energy in the consumer's food. So we're not talking about producers, we're talking about here those organisms that are consuming other organisms. And we refer to this as secondary production. Obviously with plants we looked at the idea of primary production because they're the ones that are converting that sunlight into chemical energy via that process of photosynthesis. And this is now looking at the consumers, so production efficiency of consumers. Now the efficiency of animals as energy transformers can be measured using this equation. Very similar to the other one, but it is the net secondary production divided by the assimilation of primary production. Now let's look at what that actually means. So the net secondary production is the energy stored in biomass represented by growth and reproduction. And that will be the amount of energy that's passed on. When we talk about net production, we are talking about that energy that they are going to therefore pass on. The assimilation of primary production, well, that is the energy taken in that's going to be used for growth, reproduction, and respiration. Basically, all the things other than waste. So this one does actually include respiration when we look at the assimilation of primary production. So obviously they've taken that food, they've consumed it, they've assimilated a certain amount of it. Some is lost as waste. We're not including this waste bit. Waste is over here. That's not what we're looking at. We're looking at how much they actually assimilated from that food, which can therefore be used for growth, reproduction, or respiration in that animal. Hopefully that makes sense. What that idea of assimilation is referring to there. So it's looking at that idea of taking in that food, how much of that was actually then being able to be used by the organism, excluding the waste. So when we go through this, have a go, calculate the production efficiency for the caterpillar. So using this formula here, you might want to pause it if you want to do it yourself. Net secondary production, that is the new biomass, how much they can use for growth and reproduction. That is 33 joules. When we look at the assimilation of primary production, that is this energy excluding the feces, so how much they've actually assimilated. So in this case, we've got 33 joules and 67 joules. So if we were to do and look at this formula, production efficiency is 33 divided by 100, which equals 33%. Okay, and that's going to be different to the transfer efficiency, which if you were to look at this, well, it had 200 joules, sort of the growth production there, gross production, I should say, the amount that's come in, and that would be 33 divided by 200. So if you were to do that math, you'd be able to figure out exactly how much that would contribute. So production efficiencies will always be higher than trophic efficiencies because they do not account for the energy lost in feces. And that's basically what I mentioned there. The fact is you're getting 200 joules coming in, but we're losing 100 from it. And when I look at production efficiency, it doesn't take into consideration this 100 joules that you've lost. So it will always be higher than your trophic efficiencies, which does take that into actual consideration. So if we were to do here 33 divided by 200 joules, you're looking at about 16.5% efficiency, which is obviously less than our 33% efficiency there. All right, let's have a go doing this one. A caterpillar consumes 100 kilocalories of plant material. Of that, 50 kilocalories is lost as feces, 15 kilocalories is used for growth, and 35 kilocalories is used as cellular respiration to the environment. Have a go, construct a simple energy flow diagram to the same ones as we saw before. So represent the amount coming in, show how much is used for growth, show how much is used for respiration, and how much is lost as feces. And I want you to calculate the production efficiency of the caterpillar, okay? So calculate the production efficiency of the caterpillar. So your production efficiency energy flow diagram should look something like this. You have the amount of energy that has come in, and we do refer to that as the gross. Then you have how much is used for growth, which is your net secondary production. Here you've got the 50 kilocalories that is lost as feces, and then the 35 kilocalories which is lost as cellular respiration. And this is a simple energy flow diagram. It's showing how much has come in and then how that energy is then passed on in that system. This is a more simple one. The other ones like Silver Spring that we looked at is a bit more complex with multiple different stages and steps done. The other thing you had to do was calculate production efficiency. So to calculate production efficiency, we've got our net, which is 15, divided by our assimilation of primary production. Now remember, assimilation is just looking at growth and respiration, not including the feces there. So our assimilation would be 15 plus 35, which is going to equal 50. So putting that in this formula, we're going to have 15 divided by 50 and a value of 30%. If I was to compare that to trophic efficiency, well, trophic efficiency, just to show as an example, or energy transfer, if we're looking at that energy transfer between the trophic levels, well, I had here my net, which is 15, divided by the net production of the previous level, which was 100 kilocalories, because that was how much was made available there. So 15 divided by 100, you don't need a calculator for that. You should be able to figure out that is 15%. Okay, so 15 divided by 100 times 100. Reason you don't need a calculator, boom, boom, okay, cancels each other out. So production efficiencies can actually vary among organisms. Endotherms use about 98% of that assimilated energy, so that energy that is not lost as feces, for metabolism. 98%, because as endotherms, you have to maintain that constant temperature. That requires a lot of energy, so a lot of that assimilated energy is used for metabolism. That only leaves about 2% for growth and reproduction. This is different to ectotherms, which have production efficiencies generally around 10%, so a lot higher than endotherms, because they are not using as much of that assimilated energy for metabolism. And insects or invertebrates, they have really high production efficiencies, averaging around 40%. So of that energy, they're losing losing a lot less of that energy to cellular respiration. Okay, they do not have the metabolic demand that ectotherms and endotherms, that are non-invertebrates, so vertebrate endotherms and ectotherms actually have. So in plants, it is a bit different, okay? We have looked at some of these terms, but I'll just teach you about plants as well. So in plants, production efficiency is calculated by dividing the net primary production by the gross primary production, because we're not losing that energy as feces as such, okay? So here, production efficiency, and this should be pretty simple for you, is net divided by gross. So here 200 divided by 300, which you get 2/3, so you're looking at around 66 blah blah, round up to 67% as a production efficiency there. So the energy budgets of 2 agricultural systems, 4,000 meters squared, measured over growing season of 100 days. I want you to use this data in table 1 to determine which agricultural system has the greatest production efficiency. I'm going to give you 2 marks for this one. Have a go, pause the video, I'll go through an answer now. So the production efficiency, remember our formula is net primary production, so NPP, divided by our gross primary production, so GPP. And you can see here production efficiency for our cornfield, CF, that's going to be 105.8. So this value here, our net, divide by 138, which is our gross, and that gives you a value of 77%. This is different compared to the production efficiency of our mature pasture. So we're going to have 20.7 divided by 24.4, and if you're good at maths, you'll have got 85%. Now you realize that that is high. So for 2 marks, one, that you've calculated the percentages correct, and the second mark I'm going to give you is that you actually have interpreted the question. So therefore, the mature pasture, you've given me the answer, has the greatest production efficiency. There's your 1 mark, and I'll give you a mark each for your percentages at 85% compared with the cornfield's production efficiency at 77%. That should enable you to now calculate production efficiency of both consumers, which is obviously the net production divided by the assimilated, so that's the growth or the new biomass, the net and respiration, excluding feces. And if you're looking at production efficiency in plants, well, it's the net divided by the gross, how much was actually taken in there for that plant. Looking at an energy flow diagram interpretation of a larger scale. So here's another one. This is energy diagram and data modified from that Silver Springs field experiment, just representing it in a different way for you. 3 questions. 1, determine the gross productivity of producers. 2, calculate the respiration of herbivores. And 3, identify which trophic level has the highest energy transfer. So let's go through, pause the video right now, and you can have a chance to go through the answers, which I'm about to. Question 1 was the gross primary productivity of the producers. Looking at this diagram, you'll see that the gross primary productivity of the producers is 87,000. And obviously this stands for GP, gross production, or in this one, in case of producers, it's gross primary production, which is a little different to the gross production of the other ones there, or gross productivity. Number 2, well, that was looking at the amount of respiration by the herbivores. To calculate that, you've got your total respiration and you have how much these other ones are. If you do some maths, the respiration of herbivores will equal 78,000 minus the total, which will leave you with a value of 7,816 to represent the amount of respiration of the herbivores. And number 3, to calculate which one had the highest energy efficiency or transfer efficiency within this diagram. So remember, I don't look at the producers, I don't consider them, because they are not looking at a net production from the previous trophic level, because the previous trophic level is simply solar energy. So to do the maths, I look here, I've got my herbivores. This is the amount that they've actually, their net production. So that was the net production, and this was the amount that they took in. Looking at some of this, obviously it's talking about your production, so your net production, and this one is looking at consumption, so how much they are actually consuming. So to do the maths, I've got, this is my net, divide by how much they're consuming, so 6,184 divided by 36,957 times 100 equals 16.7%. Then to look at the consumers, well, this is their net production and this is the net production of the previous trophic level. Ignore the gross production because we are focusing on always the net production. The gross doesn't take into consideration, well, the gross takes into consideration the amount lost as respiration, but we want to know how much was actually passed on or available at that next level. So we have 280 divided by 6,184, which you should have got 4.5%. And then the tertiary consumers, well, we have their production, which is 25 divided by the production of the previous trophic level, which is 280, which is 8.9%. Therefore, the herbivores, looking at this, are the trophic level with the highest energy transfer percentage of 16.7%, which is larger than the other ones because obviously we've got 8.9 and 4.5. If you got that right, well, you're doing very well at this stage. You really know what's happening. You're able to look and figure out, well, what's the production? How much is the net production? I'm going to divide that by the net production of the previous trophic level. And I have changed it up each time. All right, when I've represented that data, it has been different, which has tried to make things a bit more difficult and make you think through. But now you've been exposed to a whole different ways that they can ask this type of question for you in an external exam. That should mean that you'll have more confidence when you come to do it. Shifting gears a little bit now, we've looked at the fact that the sun provides a constant external supply of energy to Earth. But we're going to now look at the transfer and transformation of matter, not energy. So the total matter that exists on Earth is actually fixed, and resources must therefore be recycled. I know that it's not completely fixed because yes, we do get some meteorites come in and we do lose some matter as satellites, but for the most part it is a closed system when we look at matter because matter is not entering or leaving there. These cycles, these nutrient cycles, or sometimes referred to as biogeochemical cycles, well, they're the cyclic movement of key chemical elements through the biotic, so the living components, and abiotic, non-living components of an ecosystem. One of those cycles, the first one we're going to look at, is water. Now, water is essential to all organisms, and its availability influences rates of ecosystem processes, particularly primary production in plants and decomposition, looking at those detritivores and decomposers in terrestrial ecosystems. Water, very essential. You know you mostly water. You know all organisms need it basically to live. So let's look at how it is cycled. When considering these, we're going to look at three aspects of the water cycle. First one's reservoirs. So oceans contain 97% of the water in the biosphere. 2% of that is bound in glacier and polar ice caps, and the remaining 1% is in lakes, rivers, and groundwater. And some of that groundwater we can't access. So we're really, when we're drinking water, we're looking at this 1% of water on Earth that we're able to use and cycle. So this is a very important thing that we understand the water cycle. So I'm going to get you just to write down these key processes, these steps, in a bit of a flow chart, which should hopefully help you understand it. So the first bit of the water cycle is evaporation or transpiration of liquid water by solar energy from the earth, or the loss from plants for transpiration. So you can see that you're going to get evaporation from the ocean, you're going to get evaporation from the land, and you're going to also get transpiration as plants lose that water via stomata. That is going to now enter up and move into our atmosphere. The next step is condensation. As that water vapor rises, it starts to cool, which means it condenses, forming clouds. Clouds are just simply water vapor. Then you get precipitation. So we've got evaporation and evapotranspiration. We then get condensation, we form clouds, and eventually we get precipitation, just a fancy word for rain. And most of us have that annoying friend that will call rain precipitation. It's rain, but precipitation just makes them sound so much more fancier. So once you get precipitation, you're going to get runoff into groundwater, runoff back into oceans, and also across the land. So you get surface and groundwater runoff. So now we've got water that's returned to the land, returned to the ocean, returned to the plants, and then we're going to cycle all again. So that flows back up. You get evaporation, transpiration, and you can see how this water cycle takes place. So you're getting that constant renewal of water. So you get evaporation, transpiration, condensation, precipitation, runoff. Let's do it all again. So looking at carbon, the biological importance. Well, carbon forms a framework for all organic molecules essential to all organisms. Therefore, biologically, carbon is very important for us and why we are looking at these cycles. So the major reservoirs of carbon include fossil fuels, soils, sediments of aquatic ecosystems, oceans, plants, animal biomass, because every living material contains carbon, and the atmosphere. But the largest reservoir is sedimentary rocks, i.e. like limestone, like these guys here. That is the largest thing that contains carbon, hence why when you add an acid onto limestone, it bubbles, giving off carbon dioxide, because it contains that carbon. Looking at the key processes of the carbon cycle, well, it begins with photosynthesis, which removes that atmospheric carbon dioxide. So we've got CO2 in the atmosphere, photosynthesis removes that carbon dioxide, and that's photosynthesis, which might be with trees in terrestrial ecosystems, or phytoplankton or algae in some of those marine and aquatic ecosystems. So that carbon, which is now stored in the plants or the phytoplankton or the algae, is consumed and then passed along the food chain. So the rabbit eats the carbon, the lynx eats the rabbit. I should have the arrow pointing in the direction it goes. So you get those consumers. The zooplankton eat the phytoplankton, the fish eat the zooplankton, and so on. It gets passed along that food chain. Carbon is also stored as coal, oil, and natural gas as a result of decomposition. So as these animals die and the plant material die, they get decomposed, and as a result of that, you're getting that carbon stored as coal, oil, natural gas. So yes, the thing that you put in your car is a result of the decomposition of living material, which one of the things that fascinates me, when we think of oil, we think of like a lot of those Arab countries, which we know are mainly desert, but they must have had a rich amount of organic life, living material for them to have so much oil, because it's obviously the decomposition of that living material which makes our coal, oil, and natural gas. Cellular respiration by these living organisms will also return that carbon dioxide to the atmosphere, and once we're back in the atmosphere, well, that's going to start all over again. We're going to get photosynthesis, we're going to get it passing along the food chain, going to get them decomposing and respiring, so the whole thing starts again. And they're the key bits of that carbon cycle, the main things that you really need to take away and know. And our last thing we're going to focus on is the nitrogen cycle. So nitrogen is essential. What's its importance? Well, it's a component of amino acids, proteins, and nucleic acids, and is crucial and often a limiting plant nutrient. So ones that plants need, and obviously the more they have, the greater growth they can, to a point, but it is very important for living organisms. So the main reservoirs of nitrogen is the atmosphere. When you breathe in, every breath, you're taking in 80% nitrogen gas, okay? So the most thing that you breathe in from our atmosphere is nitrogen. It's also bound in soils, sediments of lakes, rivers, oceans, and in the biomass of living things, obviously, because we have proteins. Proteins contain nitrogen as well as DNA and our other nucleic acids. So the nitrogen cycle, key processes. You've got nitrogen fixation by nitrogen fixing bacteria in root nodules of plants, which remove that nitrogen from the atmosphere. So you can see it coming in here, and then you've also got nitrogen fixing soil bacteria, which are down there. So you get ammonification of nitrogen fixing bacteria in the soil, and nitrification by nitrifying bacteria. So you're getting two things going on. These nitrogen fixing soil bacteria convert it to NH3. These nitrifying bacteria then convert it to NO2 and eventually into NO3 nitrate, which can be used directly and taken in by plants from the soil. So some plants, for example, that don't have nitrogen fixing bacteria, they can still take in some of that nitrogen that's been returned to the soil through the work of these decomposers and nitrogen fixing bacteria there. So plants take those in, so you get the assimilation of plants, and this is then passed along that food chain. As each animal eats another one, they're getting that nitrogen from the previous level. But the thing that's really kicked us off is this nitrogen fixing bacteria. And you'll then eventually get the decomposition of living material, which that bacteria again start the breakdown of nitrogen, and this whole process kicks off and it starts again. One thing that also returns nitrogen to the soil, lightning, can cause a little bit of nitrogen to return to the soil there. So looking at the key processes, you get nitrogen fixation by nitrogen fixing bacteria and root nodules. You also get nitrogen fixing soil bacteria undergoing this process of ammonification by those bacteria, and then these nitrifying or nitrifying bacteria, they convert it to a form that is usable. That is assimilated or taken in by plants, passed along the food chain. When these plants and animals die, it's returned to the soil, and this whole process continues over and over. And you can see how that is a cyclic process there. This lesson, a lot to take in. Hopefully you can consider and construct those energy flow diagrams. You know what they mean, you know how to interpret them. You can also calculate production efficiency and be able to use those terms like gross and net productivity, and you know three of the main cycles. Get those different flow chart diagrams down. Make sure that you can understand what's happening in each of them. Until next time, guys,